Let me just make a few corrections to what I said in the previous lecture. There was a student up here and showed me that I've been a little bit sloppy in writing a few of the equations. So one thing that I did was that I wrote I think I wrote this where we discussed the equation describing the time derivative of the angular momentum. So somewhere along the derivation I wrote this. This should be Fji. And when I was discussing conservative systems, I wrote that for conservative systems, the force can be written in this way mathematically due to this property that the closed loop integral from one point to the same point has to be 0. What I should have done here is just to add a vector sign above the r, because in general the potential can have a directional dependence on the position vector. So if there is no vector here, it means that the potential only has a radial dependence, which is the same as a central force. So that it's just a detail. So to be completely general, I should have added a vector sign above the r. And I also received a question about the exercises in this course, the written exercises, and they are not mandatory, so you don't have to hand them in. However, I strongly recommend that you do them. If you want to get a good grade at your exam and learn the physics in this course, you have to do the exercises. No doubt about it. Okay, so we were discussing the content of the angular momentum of the system. What does it consist of? And we had introduced these various vectors. We had introduced the reference system with the origo, the center of mass, and the position vector to some particle I. And then we introduced these relative vectors, primed vectors, which essentially are the difference between the position vector to particle I and the center of mass position vector. And the reason for why we do this will now become clear. We start out again with the general definition of the total angular momentum in the system, just the sum over all the angular momenta of each particle I. And using these definitions, I can rewrite this equation like this. So I get 4 terms. If I just multiplicate out all of these terms in this equation, I get 4 terms like this. So now the task is to try to attach some physical meaning to each of these terms. What do they represent physically? Well, before doing so, there's at least one simplification we can actually do. And that simplification is to set these terms equal to 0. So please take 1 minute to discuss with your neighbor, why are these terms equal to 0? All right, any ideas? Why are these terms equal to 0? No ideas? So note that the relative vector here, Ri prime, you can write this as so it's the difference between the position vector Ri and the center of mass coordinate large R. And we also have a sum over I involved. Well, the reason is that we have actually a cancellation of terms. And we can see this by using the definition of the center of mass coordinate. So these two terms are actually 0 by definition. So we have and then recall the definition of the center of mass coordinate. So let's insert this into the equation. So we get this. Now this term is independent on I. So the only summation over I regarding this last term is related to mi. This is just the total mass of the particles in the system. So this term cancels, becomes 1. So we end up with this, which is 0, because I can rename this indices to I if I like. So that's a pretty significant simplification of this equation. These two terms cancel. So we're left with these terms. And we get this large m because the only term here which is depending on I is the mi. So the sum over I just becomes large m. And now perhaps we can say something about the physical meaning of the content of the angular momentum. This first term involves only quantities related to the center of mass. Contains the center of mass position, the total mass of the system, and the velocity of the center of mass. So this first term can be interpreted as the angular momentum relative to the origo of the coordinate system, as if all the mass of the system was located in the center of mass. So this is the center of mass term. Now what about the second term? Well, we see that it only involves relative vectors. It involves the relative position of particle I relative to the center of mass, and the momentum of particle I relative to the center of mass. So the last term actually describes the angular momentum relative to the center of mass. Okay, so let's try to visualize this physically. Let's say my hand here is the origo of the coordinate system. This is the system with all the particles. If this is moving in some kind of orbit without changing its position relative to its center of mass, only the first term is non-zero, right? Because there's no relative motion of the particles in the system relative to the center of mass. It just moves like a whole. But there is motion relative to my hand. However, if I now take this compendium and see if I can do this, if I spin it while it rotates, then I have two kinds of rotation. I have one rotation relative to the origo, but I also have an internal rotation relative to the center of mass. So it kind of spins simultaneously as it rotates. So that's the second term, because it only consists of the relative position and the relative momentum. So we could rephrase this as the internal spin of the system, we could say. So yet another scenario is that if the center of mass is not moving relative to the origo, but only spins around itself, then only the last term is non-zero, whereas the first term is zero. Do you have any questions related to this? Okay, so we see that the total angular momentum of the system can be divided into two parts, the internal spin and sort of the angular momentum of the system as a whole, represented by the center of mass. Now the question is, can we do something similar for the kinetic energy of a system? Well, it turns out that we can actually split the total kinetic energy of the system again into one center of mass part and one sort of internal part. So again, I use this definition of the relative velocity vector. So what really enters here are the velocities of particle I, Vi and Vi. But I rewrite this in terms of the center of mass velocity and the relative velocity of particle I with respect to the center of mass, just as we did for the angular momentum. And if I just do the multiplication here, I get the following. So I also get 4 terms, but 2 of them are the same and combine into this term. As we saw just 5 minutes ago, this last term is 0 by definition. So the kinetic energy can be rewritten as a center of mass term, the velocity of the center of mass as if all the mass was gathered into one point and moving, in addition to the relative velocities of the particles with regard to the center of mass. So then I have one question. Let's say that we're dealing with a rigid object. This desk is rigid enough for our purposes. It means that it's solid. I can't deform it. Not easily, anyway. So this point will always be fixed compared to this point, for instance. It's rigid. Does this mean that the second term is 0? No? Why not? Right. So just to repeat for the recording, if you rotate the particles, they will still move. So this term not only describes a physical deformation of the object, but it also describes a relative rotation of the particles compared to the central mass. So similarly, you can actually have an object which is standing still, but if it's rotating, it still has kinetic energy. And that is precisely what is described by this term. So this is the center of mass term. And this is the internal kinetic energy, for instance, describing rotation. Okay. We'll now try to say something about a concept which is often used in realistic systems, namely constraints. If we were to describe, for instance, a system of a gas, a system of particles trapped in some container, we would have to use some constraints, namely the fact that the particles cannot move outside the container, right? So there's some kind of boundary condition at the walls, which prohibits the particles from escaping. So how do we take into account constraints when describing and wanting to solve various mechanical problems? So one example is a gas with particles in some container. Another example is some ball rolling down a hill. And I use these two specific examples because I want to introduce a type of classification for constraints, because you can have different types of constraints. One type of constraint is known as a holonomic constraint. And a holonomic constraint can be written the following way. It's a function of the particles R1, R2, etc., and all the particles in the system, and possibly even time. And it has to be equal to 0. An example of such a constraint is a rigid body, because the equation describing some rigid body can actually be written quite generally like this. So this expresses that the relative position vector, the magnitude, since we square here, the magnitude of the relative position between 2 points in the rigid body has to be the same. It means that you can't deform the body. You can still have a rotating body. You just can't deform it. You can't change the distance between the particles. This has precisely the form of a holonomic constraint, which can be made obvious by writing the equation like this. Well, if you have holonomic constraints, you might have guessed that it's also possible to have non-holonomic constraints. And non-holonomic constraints cannot be written like this. So if you consider this ball rolling down the hill, this is actually an example of a non-holonomic constraint. To make it a little easier, let's assume that this hill incidentally has the form of a perfect circle. With some radius a. So then the physically allowed space where the ball can move is everywhere here except inside the hill. So basically, if R describes the position vector to the ball, then R squared minus A squared has to be greater than 0. If it's 0, it's moving along the hill, but if it's jumping, for instance, bouncing, then it's greater than 0. So basically, this is a non-holonomic constraint, because you don't have an equality sign here, you have an inequality sign. So let me also just mention briefly 2 types of classifications which are related to the time dependence of the constraint. You have something known as rheonomic constraints, which are time-dependent constraints. And you have scleronomic constraints, which are time-independent. So these are a lot of words. What we'll be dealing with mostly are holonomic constraints. But it's good for you to be aware of these various classifications. So this was basically so far, well, up to constraints, mainly a repetition of stuff which I think most of you have seen in some form or another previously. And now we're actually moving towards actually our first encounter with this earlier mentioned Lagrangian formalism, which will prove to be a very useful tool for us and it sort of gives us a general prescription for how to address problems in mechanics, as a general procedure for how to solve them. Related to this Lagrangian formalism is an important concept known as generalized coordinates. So again, we confine our discussion to a system of many particles. Assume we have large n particles. If you allow all of these particles to move in 3 dimensions, we will have 3n number of independent coordinates. But let's say we want to incorporate now constraints to the system. We assume that there are some kinds of constraints which are valid for our system. And let's say we have a number of k constraints, and we assume that these are holonomic for simplicity. So we assume that there are a number of k constraints which can be written like this. So it means that if we have originally 3n independent coordinates with k holonomic constraints, we have 3n minus k independent coordinates in reality when taking into account these constraints. And we denote this new set of independent coordinates as qi. So that if Ri are the original 3n degrees of freedom, then qi are these new independent degrees of freedom when taking into account these k constraints. So let me write this. So we start with a description of the system where each particle is described by Ri. So we have R1 describes particle 1, R2 describes particle 2, etc., up to particle n. Sorry. So when we take into account the constraints, it means that all of these original degrees of freedom are no longer independent. They can be described in terms of these new generalized coordinates qi. But we see that we have 3n minus k degrees of freedom which are independent. So it means that not all of these R1, R2 up to Rn can be independent. You see what I mean? So these, the q's, are now the independent coordinates where the constraints have been taken into account, whereas the r's are the original, it's the original description of the system without taking into account the constraints. So you can think of this set of equations as a set of transformation equations taken from the original description to these new generalized coordinates, or vice versa, by including the constraints in the system. So this might seem a bit abstract, so let's consider a concrete example. So what we have here is, for instance, a ceiling, and we have a double pendulum. So we have one spherical ball, for instance, hanging from the ceiling by some rope, and attached to this one is a second ball with another rope here. And let's assume that this rope is in fact a bar, which is rigid, so you can't deform it. Now, in principle, if this system could move in 3 dimensions, we would have, how many degrees of freedom would we have? 2 particles. 6. 3 for each particle. Let's confine the discussion to a plane. So these particles are now only allowed to move in a plane. How many degrees of freedom do we have then? 4? Why? Exactly. So in principle, for this system, we should have 4 degrees of freedom. However, as we fix the distance here by saying that this ball is connected to the ceiling by a bar, which cannot be deformed, we're removing 1 degree of freedom. We are removing 1 degree of freedom for each ball. So DOF, degrees of freedom, is that we have 2. So we're doing this by saying that the distance between these points and these 2 points are fixed. So the only degrees of freedom we have in the system are in fact the angles here, θ1 and θ2, which are describing how these objects are moving relative to each other. So the generalized coordinates for our system here are θ1 and θ2. Let's try to see how this relates to this set of transformation equations. Let's say that origo for our reference system is located here. So if the position of particle 1 just wanted to make it a right-hand system. Okay, so x is going down, y is in this direction. So we see then that the x position of particle 1 should then be r1 cosine θ1. y1 should be r1 sine θ1. These are just polar coordinates. But in fact, this is just L1. Cosine θ1 and L1 sine θ1. So if we were to write this transformation equation for our system, we should have you see that it's only a function of θ1. All right? In principle, it could have been a function of θ2 as well. But it's only a function of the generalized independent coordinates of the system. These 2 coordinates are independent. All the other coordinates are depending on each other. So do you see the difference between the original set of coordinates which are used to describe the system and the set of independent generalized coordinates when you take into account constraints in the system? Okay, I see some nodding heads. Right. Right, having introduced these, the notion of generalized coordinates, we're actually ready to take the step on to deriving the Lagrange equations, which will be the equations you use most in this course. Oh, that was beautiful. Equations. In addition to these generalized coordinates, we have to introduce a concept known as a virtual displacement. So I'll just define it here. So a virtual displacement is defined as an infinitesimal displacement of the coordinates of the system which are in accordance or allowed by any possible constraints that may be possible in the system. So if we revert to our example of the ball rolling on a hill, an allowed virtual displacement would be up or along the hill, but not into the hill. That would be in, that would not be allowed in terms of the constraints of the system. Assume first that we have a system which is in equilibrium. And by that I mean that the net force acting on each particle is zero. And if each force is zero, then it's trivial to see that the sum of each force dotted with this virtual displacement vector also has to be zero, because each term is zero. And let me now assume that this total force Fi, this can be split into two parts. So I've split the total force acting on particle I into an applied force and a force coming from the constraints of the system. So for instance, a gas with particles inside a container, in this context, the constraint force would be the force acting on the particles by the wall when they're bouncing against the wall. Whereas an applied force would be if we change the pressure in some way, for instance. So this part of the force stems from the constraints, and this is an applied force from us, the observer, for instance. Yep.
They are vectorial force.
Yes. Okay, I think we'll call it there. So remember, the guidance hour is on Friday from 2 to 3.